How do integers form Pythagorean triples? Imagine a right triangle with whole number sides. How do those numbers fit together perfectly to satisfy the Pythagorean theorem? Well, that's where Pythagorean triples come into play. These are sets of three positive integers that make the equation a squared plus b squared equals c squared true. The most famous example is 3 for and 5 because 3 squared plus 4 squared equals 9 plus 16, which totals 25, and that equals 5 squared. When these three numbers fit the equation exactly, they form a Pythagorean triple, representing the side lengths of a right triangle with integer sides. Integers from these triples in two main ways. First, there are primitive Pythagorean triples. These are the simplest sets where the three numbers share no common divisor other than 1. For example, 3, 4, and 5 are primitive because they don't all share any common factor. Another primitive triple is 5, 12, and 13. These are called primitive because they are the most basic building blocks, and no smaller numbers can be divided evenly into all three. The second way is through non-primitive triples. These are just multiples of primitive triples. For example, if you multiply each side of 3, 4, and 5 by 2, you get 6, 8, and 10. These still satisfy the Pythagorean theorem because 6 squared plus 8 squared equals 36 plus 64, which is 100, and that equals 10 squared. So these are not primitive but are still valid triples because they are scaled-up versions of the basic set. Now, how do mathematicians generate these triples systematically? They use a formula involving two positive integers, m and n, where m is greater than n. The formulas are equals m squared minus n squared, b equals 2 times m times n, and c equals m squared plus n squared. When m and n are coprime, that is, they share no common factors, and not both odd, this formula always produces a primitive Pythagorean triple. For example, choosing m equals 2 and n equals 1 gives a equals for minus 1, which is 3, b equals 2 times 1, which is 4, and c equals for plus 1, which is 5. So, the triple 3, 4, 5 is generated directly from these two numbers. Because the Pythagorean theorem relates directly to right triangles, these triples give us exact measurements for triangles with integer sides. They are useful in construction, design, and even in understanding the relationships between numbers and shapes. In essence, integers form Pythagorean triples by satisfying the equation a squared plus b squared equals c squared, either as primitive sets or as multiples of these primitive sets, often generated through formulas involving pairs of numbers. This connection between numbers and shapes helps us see how geometry and arithmetic come together in a simple yet powerful way.